Oh, we are just cruising right along here. We are on to section 8.4. Looks like I scrolled up too far. 8.4, part 2. And in this section, we're going to be talking a little bit about equilibrium, using vectors to find a force that will keep an object at equilibrium. So we've got a couple examples that use this. So I just want to go through the steps for that. So first thing that we want to do is convert all vectors into component form. Then we're going to add all the vectors together, which finds our net force. And we're going to work with this here in just a second. So F net is what we call the net force. That's how we label it. And all that means is that we are going to add all vectors together. So the sum of the vectors is the F net. Okay? And then we are going to add on a fourth force, is what this is called, a fourth force, or F sub 4. The reason that is because on the example that we're doing that on, there are 3 forces being put together, and they want you to find a fourth force that will equalize the force, make the object feel no force at all. So it's called a fourth force, and then we set all 4 of those forces then equal to 0 and solve for this x and y. And that finds our force that sets our object at equilibrium. Step number 3, solve the equation for x and y. And it's going to be in component form. If we need to find the r, or the magnitude, and the theta, then we can also continue on to that. To find your magnitude, that is equal to the square root of x squared plus y squared. And then find theta using our equations x equals r cosine theta. Double check your quadrants, make sure you're in the right area. Then use y equals r sine theta to check your solution. You have to now have the magnitude r and the direction theta of the vector needed to keep the object in equilibrium. Okay, so we'll move on to the examples now. Alright, so we skipped example number 1 because example number 1, we don't really have any homework assignments like that, and it goes a little bit deeper into what we need to go into. And just with the way things are this year, we're going to skip out on example number 1 for today. So example 2, we have 3 different forces act on an object. They are force 1 at -2, -1, -3, 2, and -1, -6. We want to find the net force. So remember that we said the net force is the sum excuse me, of all forces. So F net is going to be F sub 1 plus F sub 2 plus F sub 3. So we could really just draw a line underneath here. Add all of our x's down. So that looks like we're going to have -6. And then -5. And that is what we call our F net. Okay, so F net is going to be -6, -5. Then for part B, it wants us to find the fourth force, F sub 4, that would be needed to added so that the object feels no force. So for that one, we are going to take the sum of the F net, or the sum of all of the forces, which we already found to be -6, -5. And then we're going to add on some unknown force, xy, that will cause this object to be in equilibrium. That's what we call it. So feel no force at all. So what will happen here is we need to subtract this force from both sides. Since it's kind of hard to subtract forces, I'm going to go ahead and let's just multiply this by the scalar -1 and then add to both sides. So then we're going to add that to both sides. So we end up with our fourth force being the vector 6, 5. All right, example number 3 is another application of how we can use these vectors. So in example number 3, we have an airplane that is heading north at an airspeed of 550 kilometers per hour. But there is a wind blowing from the southeast at 70 kilometers per hour. The plane will end up flying how many degrees? There should be a space in there. How many degrees off course? And the plane's speed relative to the ground will be blank kilometers per hour. So let's start by looking at some pictures of this. I'm going to draw a couple things. So first of all, we have our airplane, and our airplane is heading due north. It's got it going north at 550 kilometers per hour. And at 550 kilometers per hour, that is, I can't turn my thing sideways. That didn't work. Okay. 500, I just can't write sideways. Oh, hold on. Okay, 550 kilometers per hour. So that'll be the magnitude of that vector, and its direction is due north at 90 degrees. So that's going to give us a vector, component vector of 0, 550. Okay. Now we also have the wind that is blowing out of the southeast. So I'm going to draw a little weather vane up here to help us figure out what's happening with this wind. Okay, so this is our wind. Up there too high. So we've got north, east, south, and west. Well, it says that our wind is blowing from the southeast. So coming from the southeast means it's going to be blowing in that direction right there. And it is going to be blowing at a rate of 70 kilometers per hour. Okay, so at 70 kilometers per hour, that's kind of small. Let's draw that again over here. We would have a vector come in this direction. It's going to be 45 degrees off of the x-axis. Or if we come from this direction over here, that's going to be at 135. So that's going to be what we're using for our theta. And it has a magnitude of 70. All right, so I want to know what the component form of this vector over here. Now this is just looking at the wind. This is not how the wind impacts the airplane right now. So this value here is going to be 70, which is our magnitude, times cosine of 135, and then 70 sine of 135. So for just our wind, we are going to get the vector, and this is going to be at the point negative 49.497, and then positive of the same thing since it is at a 45-degree angle. These will most likely always be your same numbers. And then 49, so we got one is negative, one's positive, and 497. Okay, so that's our component form of our vector for just the wind. Now we need to know what happens when we apply that wind to our airplane. Okay, so let's come back over here. Let's put the wind in red. I'm going to erase my numbers again because that's going to be in my way. All right, now I am going to apply this wind vector to my airplane. So we're going to come out here to the end of our airplane. We're adding these vectors on. So I'm sliding this wind vector out to the end of my airplane. This still has a magnitude of 70 here. But now we're going to add on a third vector, which is the sum of the airplane's force and the wind's force put together. right? So I want to know what happens after the wind is applied to the airplane. What does that do to my airplane? So I'm going to add the vectors. I had my airplane vector, which is in purple, right here. My airplane vector was the vector 0, 550. Now I'm going to add on the wind vector at negative 49.497 and positive 49.497. Okay, once I add those two vectors together, I can actually do that one without a calculator. It's not 0. Once I add those two vectors together, we get the vector negative 49.497 and then 599.497. Now this is the component form for my new vector here. So this is what happens to my airplane. This is where it's actually going to end up. Instead of at the point 0,550, it's going to blow us this far off of course. Now we want to know how many degrees off course it is. That means I need to find the theta value. Well, I know what x is and I know what y is. So let's go ahead and use those to find what theta is. So x equals negative 49.497, and that's equal to, oh, we need our magnitude. Let's come over here and find our magnitude really quick. So our magnitude is going to equal the square root of x squared plus y squared. So negative 49.497 squared plus 599.4977 squared, and then take the square root of all of that. And I'll just tell you what it is. After I calculated that, I got 601.537. Okay, so 601.537. Now, since we are working, that's our magnitude. Sorry, finish this thought. Okay, so magnitude times cosine theta is equal to our x value. Okay, so we need to figure out what our theta value is. This is the theta that we are trying to find right here. Now, because we are working with cosine, this quadrant 2 is going to give me the first solution of the cosine of a negative, or the arc cosine of a negative value. So I just need to find my first solution here. So divide both sides by cosine, or 601.537. Then take the arc cosine of both sides, and we want the first solution, which that first solution is 94.72. But that's not going to be our answer. We've got to be careful here, because what this gives me is the value from the x-axis all the way around. We only want the part from the y-axis and around. So we need to subtract 90 from that to get the answer that I want. So once we subtract 90 from that, then we find that the total degrees the airplane off course is 4.72 degrees. So that's my answer that I'm going to put in. Oh, and I'm almost out of time again. This goes by way too fast. The airplane speed relative to ground, that is going to be my magnitude. So I already found that. Thank goodness. And go back and make sure that I'm right on all of these. Yep, so everything looks really good.